Hey everyone, this is lesson 12, differentials, and it's going to just give us some applications here for the equation of the tangent line. So whenever you see find the equation of the tangent line, we already know what that means, right? Y minus y1 equals m times x minus x1. But a lot of the times we see that phrase as local linear approximation. And again, all that means is just equation of the tangent line. Okay, so let's take a look at some examples. Obtain the local linear approximation, or sometimes they'll just say linearization of, and they give us this function here at x equals 2. And we want to use the result to estimate f of 2.1. So if we want to do that, ultimately what we're doing is we're finding the equation of the tangent line, and we're using that to make an estimate at 2.1. Okay, so let's start first with finding the derivative. Okay, if we take the derivative of this f of x function, we're going to get 6x minus 4. And now, if we want to take this derivative at x equals 2, I'll just go ahead and plug in 2 into my derivative. And this will give me the slope of the tangent line. So when I plug in 2, 6 times 2 is 12, and 12 minus 4 should give us 8. Right? Remember that 8 is just the slope of the tangent line. So in addition to the slope, we need a point. So here we know that x is going to be 2. So when x is 2, what's the y value of the function, right? So remember, we just want to take the 2 and plug it into our function here. So that's going to be 3 times 2 squared minus 4 times 2 plus 1. And when we do that here, we just evaluate the exponents first. So this will give me 4 times 3, which is going to be 12, minus 8 plus 1. We know that 12 minus 8 is going to give us here 4, and 4 plus 1 is just going to be 5. So in other words, when x is 2, the y value here is 5. So we have our point and we have our slope, right? So with that, we can write the equation of the tangent line. So our equation is going to be y minus 5, which is equals to the slope, and that would be times x minus 2, okay? All right, so this is the equation we want to use as our starting point. Okay, so now when they ask you to use your result to make an estimate for 2.1, I would just want to plug in 2.1 into this equation here. Okay, so you can choose to move the 5 to the other side so that your equation ends up looking something like this: x minus 2 times that 8 plus the 5, and then now when we go to plug in this 2.1, we make our estimate here, which will basically be f of 2.1. Right? Again, this is just an estimate, but this will be 8 times 2.1 minus 2, and then plus 5. Now, we can leave our answer like this. We're going to see this a lot in FRQs, and this is how we're able to leave our answer. Because remember, we don't really have to simplify this. Okay, so this is the answer for the estimate at 2.1, and to obtain the local linearization, and then we could leave the answer like this. That's really just the equation of the tangent line. Okay, I'm just going to do a couple more examples. Find the local linear approximation, which again just means equation of the tangent line, with our f of x function, this time at x equals 6. Okay, we won't use that to make an estimate as well, but let's start by taking our derivative. And so when we take our derivative, we get 2x minus 5, and now we want to take 6 and plug it into our function. Into our derivative. So 2 times 6 is 12, and we know that 12 minus 5 should give us 7. And so 7 really is just the slope of the tangent line, okay? Now, if we know that when x is 6, when we plug that into the function, that'll give us the y value. So this will become 6 squared minus 5 times 6 plus 7. And then from there, we're just going to simplify this. So let's see, that's 36 minus 30, and then plus 7. 36 minus 30 should be 6. And then we know that 6 plus 7 should give us 13, right? So that means that when the x value is 6, the y value is 13. So I'm just going to go ahead and write this as a coordinate, and that means that we have our point and we have our slope right here, okay? So the equation for the tangent line, or the linearization, if you will, would be y minus 13, which is equals to the slope, 7, and then times x minus 6, all right? So that's how we'll start this one. Let me move that 13 to the other side just to show a different way of writing the same equation here. And the reason for this is because now, if I want to, I'm going to box this because that's part of my answer. If I want to make an estimate at 6.2 for my tangent line, I would just say, hey, I'm going to plug in 6.2 into that function, right? Which I guess we could plug it in right here. That'll be 7 times 6.2 minus 6 plus 13. Now we can do the math here, but a lot of the times we can just leave our answer like this. There's no need to simplify, okay? All right, that's all you got to do here, and that's how we could take our estimates, okay? All right, so there's a couple other things I want to talk about. Let's do some more applications. And the other application that I want to discuss is what happens when your function is concave up. Well, where would the tangent line fall? So let's just say that our point that we're looking for is, x equals whatever, something like that. And so our tangent line might look something like this and like this, right? And so the tangent line falls below the curve, okay? And so I would always say that something like this, where the tangent line falls below the curve, is an underestimate. Anytime we make those estimates, we would say that they're an underestimate, okay? And if we had to explain or give a reason, we could say because the tangent line falls below the curve. Okay, that would be a perfect reason. Mentioning the concavity, mentioning that it falls below the curve because the function's concave up, that would be a bonus there. Okay, that's awesome. Okay, now if your function's concave down, think about where your tangent line goes. So I'm just going to draw a point here, x equals whatever. Okay, and then we have here this tangent line that might look something like this. Okay, and then our tangent line is above the curve, right? And so because above the curve, all these estimates would be an overestimate. All right, so I'm going to write here, these are overestimates. And I'm going to write because the tangent line is above the curve. All right, and again, it's above the curve because our function is concave down. Okay, so that's really important. So when could you see this? This is actually also pretty common as part of these FRQs, and they're usually like part of the same question, okay? So let's take a look. Let's say that f is concave up on its domain, and we know that f of 4 is equals to 5, and we know that f prime of 4 is equals to 3. What is the estimate for f of 3.8, and this is an estimate, right? Using the local linear approximation for f at x is equals to 4. So first thing we want to do is write that local linear approximation, aka tangent line equation, right, when x is equals to 4. And the cool thing here is they actually already gave us the x and y value. And x is 4, y is 5. Okay, so when x is 4, y is 5. Also, we know the slope at x equals 4. At x equals 4, the slope is 3. So we have all the information we need to write the equation of the tangent line. So that's just going to be y minus 5 equals 3 times x minus 4, right? So if I move this 5 to the other side, I would get 3 times x minus 4 plus 5, right? And that could be the equation that we use now to make our estimate, right, which is of f of 3.8. So I'm just going to go ahead and say f of 3.8 is equals to, that's 3 times 3.8 minus 4 plus 5. Now, I'd hate for anybody to add this up the wrong way or subtract this the wrong way. So that's why we say, hey, just leave it like this, okay? All right, so we got our estimate. That's done, believe it or not, okay? Now, is that estimate an over or an underestimate? And then it says explain. So you know how it mentioned that the function was concave up? That means that you can imagine any function that's concave up and the tangent line falls below it. So that means that our estimate, f of 3.8, is going to be under this curve, which basically means it's an underestimate, okay? So I'm going to write here f of 3.8 is an underestimate, because f is concave up and the tangent line, let me be very specific, and the tangent line at x equals 4 falls below the curve. Okay, so that's how we can do this. F of 3.8 is an underestimate because F is concave up and the tangent line at x equals 4 falls below the curve. All right. Let's keep looking at some other stuff that we'll see. Okay, now there's some interesting notation that might come up over time, so let's talk about that. So differentials is the name of this section here, right? And we might see this stuff as change in x, change in y, or we might see dx and dy, right? Which we know just means derivative, right? But this represents a very small quantity that corresponds to a change in a number. Okay, so that's ultimately sensitivity. It's an interpretation of the derivative describing how small changes in the input variable produce changes in the output variable. So for small values of change in x, we can approximate change in y by the following formulas. If you see change in x, you can always say that that equals to dx. And then if you see change in y, look at that. That almost looks like your slope times x minus x1 minus the y1 value that we moved to the other side. So this is kind of like that tangent line equation over here, but that's change in y, right? And then dy equals just the derivative of that f of x function, right? And then dx at the end of that. So we're going to see this notation a lot, okay? But let's do some application questions here. All right. I know this graph is very busy, but ultimately when you have x and then x plus change in x, that's your change in x right there. And then, of course, you have your change in y between those two values, and that just means change in x over change in y. We see that a lot with slope, okay? All right, so here's our example. So it says the function is equals to x squared. Find dy and change in y when x is equals to 1. That's important. Oh, and we also know that dx is equals to the change in x, which is equals to 0.01. All right, so these are the three formulas I gave you a couple slides ago. And so I just want to talk about the, let's do an easy one here. Well, this one I think is the easiest one to start with, right? Let's do dy, right? So dy is going to be really just the derivative of this f of x function, and we'll throw that dx at the end of that, okay? So what is the derivative of this f of x function, right? Well, we see if we use a power rule, we end up getting 2x, right? And then we say dx, right? Well, what is dx? Ooh, they gave that to us, right? That's just going to be 0.01, so I'm going to multiply that. There it is, okay? All right, now it does tell me that when x is 1, so I can actually take 1 and plug it in here. So that gives me 2 times 1 times 0.01, okay? And when I multiply all this together, let's see, we get 0.02. Okay, so that is dy. Now this might come up in another one of our formulas, but I don't believe it does, right? Okay, so now let's see, we had to find dy, so that's done, but we also have to find change in y, right? So let's work on that one. And that's this number 2 formula that I have here, okay? All right, so how do we find that? Well, we know that the formula says, hey, change in y is equals to f of, that's x plus change in x minus f of x. All right, so I'm going to start by plugging in everything I have first. I know that x is supposed to be 1. I know delta x is equals to dx, and remember we said dx was really equal to 0.01, okay? And we also know f of x was given to us, that's x squared, okay? So I'm going to start plugging everything in. So this really is going to give me f of, that's 1 plus 0.01, because again, that was just given to us, all right, minus, and then we know that f of x was given here, that's x squared. Oh, x squared, if I plug in 1, well, what's 1 squared? 1. Okay, all right, let's do the math here. We are going to add these two values together, so we get f of 1.01 and then minus 1. Okay, so since this is really just evaluating into the f function, I'm going to plug in 1.01 into the f of x function right up here at the top, okay? And let's see, if I do 1.01 and then square it, that will give me 1.0201, and then I want to do minus 1. Okay, So let's see, when we subtract those two values, we get 0.0201. We double check that. 0.0201. That's right. Okay, and that will be the final value there for that change in y. Okay. All right, so this is how that works. It's just one of those application questions, not too common, but just so you can kind of play with the formulas a little bit. Okay. All right, your assignment for today coming out of the black book. Remember, you can use CalcChat to check your answers. I encourage you to do that, but in order to do so, you need to see what section page 240 comes from. All right, everyone. Hope lesson 12 wasn't too bad. Enjoy.